So, okay, welcome everybody to our second lecture on convex analysis. So there's a poll. So there's a poll in the chat. So since we're doing convex analysis, and one of the prime applications, at least for me, is convex optimization, we would also like to develop a few algorithms to solve problems relying on convex analysis. And so algorithms without implementation just feels like, you know, it's just not the full thing. So, however, this is not a lecture about computational mathematics or something. So I would just like to know which programming languages can you work with. So I have just four things to offer: either MATLAB and Octave, or Python, or C, or probably even Julia. Or maybe if you don't have any programming experience with mathematical algorithms, you may also take none of the above. So so in case you can program in a different language, maybe also let me know. Okay, so because it may happen that we'll have the first implementation exercise on the next exercise sheet. However, this will then be a bonus question. Okay, so no votes up to now. Actually, I don't know if anybody is listening here, but we record everything anyway, so okay. And then tomorrow morning we had the first exercise class, and there's another question by Max about if you should choose a different time for the exercise class. So there's a doodle. Please follow the link, and then we'll see how we do it. Okay. What should I? I forgot one thing. Just a second. So and regarding programming languages again. So actually, I would be fine with submissions in basically every programming language. No, not every. Most programming languages. But I could only offer kind of debugging or correction of code for a few languages. So and then Max can offer to have a closer look at submitted code in MATLAB, Octave, and Python. I could offer to check code in Julia and closer. And for other languages, I need instructions how to run the code, and I could only check if the code would produce the right outcome. Okay, but that would probably be fine either way. Okay, so where were we? So we had all the notions on the first notions on convex sets, affine sets, affine combinations, affine independence, and related to that the relative interior. Okay, so now let's introduce for today the two more classes of convex sets, which will be important. So second lecture is about hyperplanes and cones. So, and this is not enough for the full lecture. As far as I see, there will also be a little bit on orthogonal projections onto convex set in the end. So first, the notion of a hyperplane. So the notion of a hyperplane is, so a hyperplane should be an affine linear space of dimension d-1. So we are in d-dimensional space, and any affine space of dimension d-1 is a hyperplane, and we can describe hyperplanes in different ways. And one of them is if we have one vector x0 from Rd and another p, both in Rd, and the p is non-zero. So here we have some vector x0, and we attach the vector p to this vector x0 pointing into the direction of p, and then the hyperplane defined by these two quantities would be that one here, which is perpendicular to p and passes through x0. And we would usually not encode hyperplanes by these two quantities. Yeah, because, well, this is kind of ambitious. So you could also take this x naught here or x naught over there. All these things would work. So what we do is we define the inner product of p and x0 by alpha and use this. So first, probably, what is the set here? The set is the set of all these vectors here, which go from x0 to here. Yeah, and all these vectors which are here. And so these vectors should be perpendicular to p, and this just means that p in the inner product with x minus x0 should be 0. And the set of all x which satisfy this is this hyperplane here. Okay, and of course, with this abbreviation, this is just p times x equals minus alpha, so like this. And so we define the hyperplane with normal vector p, and kind of offset alpha is defined as the set of all vectors x, such that this is 0, or put differently, inner product of p and x is equal alpha. So this passes through x naught. Okay, so these are affine sets because they are affine sets. What is nice about hyperplanes, it's very simple to project on these planes. So if we have some point here and want to find the projection of this point onto this hyperplane here, this is hyperplane HP alpha. So it's pretty clear what we need to do. We need, so if this is our x, we need to a little bit screwed my picture anyway. So we need to move from x into the direction of p, positive or negative. And how fast do we need to move? We need to move, as long as this equation here is fulfilled. So writing out what this means, you will get fairly easily. So this is our x hat, so projection, and orthogonal projection of x onto HP alpha is then go from x into the direction of p. So, and then we need just to find a scalar, and the scalar turns out to be p times x minus alpha divided by p squared. So this is what the x hat is. And you can check this. So orthonormality here, or orthogonality, is clear because this is just p. We add some direction of p to the x, and it's very simple to check that this guy actually lives on the hyperplane. Just take this inner product with p of this guy here, and you'll see this evaluates to alpha. Okay. So there's more. We have the so-called associated half spaces. So affine sets are convex. That's clear. So these hyperplanes. So this is a hyperplane. Hyperplanes are convex, and the half spaces are then just defined by using appropriate inequalities here. So HP alpha plus is then the set of all x in Rd such that px is larger or equal to alpha, and HP alpha minus is the same thing with smaller or equal. So, and it's clear that these are closed sets by just here, because you have the kind of inclusive inequality. So this is a closed set, and the inner product is continuous. And actually they're also convex. So where are they? Maybe I just draw that again. We have our vector p here, and then this guy here plus what's on the side where p points to. Just to come to that, and the negative one is the one the set which lives here. This is HP alpha minus, and the green above here is HP alpha plus. The normalization by p squared, norm of p squared here. Oh, actually, it's the 2 norm, and I think in this lecture I should always be careful that is which norm which is which. Yeah, we have to normalize this. Of course, you can forget about it if p is normalized. So if p, but we did not do so. So this p can be any vector. So it's I call it normal vector, but normal vector just means it's orthogonal to the set. So it's not normalized. So normal in this context means orthogonal. And this will be important in the following. We will talk about normal cones and normal vectors and tangential vectors. So just as a tangential vector is not normalized by default, also normal vectors are not normalized. They are only orthogonal. It's a little bit of bad wording, I agree, but so the norm of P is not assumed to be 1 here. It can be any vector, it just have to be non-zero. Yeah, it's good to know that it's like this. And in many cases, the half spaces or hyperplanes are not defined by vectors which are normalized. Okay, yeah, but good question anyway. So P is not assumed to be of norm 1. We only assume P is not 0. Okay, so okay, and these half spaces will be pretty important because what it turns out that there's this outer characterization of convex set. So we have this inner characterization where we say a set is convex if we have for any 2 points that the connecting line is in the set, and the outer characterization is that the convex set is the intersection of all the half spaces which contain the set. Yeah, so if you just by illustration, that's pretty clear. So if this is our convex set, and so if we consider all half spaces, which so these half spaces here and these half spaces which contain this set, and if we intersect all these, we get exactly this set here. Okay, yeah, and we're going to prove this with the help of separation theorems later on. Okay, so if we intersect finitely many half spaces, so we take just finitely many of these, so this will not be a round convex set, they have a lot of corners, and these sets will be called polyhedral set. So if C is polyhedral, if intersection of finitely many half spaces. So, and polyhedral sets are convex because half spaces are convex, and intersection of convex sets is convex. Okay, what's also important is, so can be written as follows. C is then equal to all the x such that we have ax less or equal b and bx equals d for some a, which is let's say n by d, I guess, yeah, some b in Rn, some capital B in Rm times d, and some c, which is in Rm. So why is that? So first, actually this is not really needed because any inequality can be, every equality can be written as two inequalities, one this way and the other way around. So we could hide this in this here. So we only need to, so if we have these, we could also hide it in here. And then you can see that every kind of, so first this is component-wise. So this is an n vector, and this is an n vector, and this means that this the ith component of this guy is smaller or equal to the ith component of that guy for all the I. And then you just need to see that each of these inequalities here is just of this form here. It's one of these negative half spaces. Because it's kind of the ith row inner product with x is larger or smaller equal to the ith entry of b. So since we want to have all these inequalities fulfilled, it's just intersection of these sets. So that was the proof that every polyhedral set can be written like that. Okay, another thing we're going to need is affine functionals. And basically that's functionals. That runs through the full the full lecture. If there's a convex set, there's often associated, or the notion of a type of convex set, there's often associated a notion of a convex function. So we have, so these are affine sets and hyperplanes and affine function and half spaces, and now we have affine functionals, and they are of the form f of x is equal to px plus alpha. So these are affine functionals for under the same assumptions as here. Yeah, and so affine functionals and hyperplanes have something in common, so they're related. And so one thing, yeah, let's see how we do it. So one thing is, so that the level sets of the affine functionals are of course always hyperplanes. That's clear. If we set this equal to some beta, we get all these hyperplanes. But there's another one, and this goes like as follows. So if we now consider a hyperplane in Rd plus 1, so in Rd plus 1, so one more space dimension, we can write down a hyperplane as follows, and now we split up the vector into the first d components and the last one. So this is a vector in Rd plus 1, means that this xd is in x prime is an Rd vector, and then the defining equality for hyperplane can be split up in p prime times x prime plus p d plus 1 x d plus 1 equals alpha. Okay. So and this is what we often do, that we kind of work in the space Rd plus 1. If you have a convex function on Rd plus 1 on Rd, mapping Rd to R, its graph lives in Rd plus 1 dimensions. So this sets are so sets and splitting up like this will be used many times. And such a hyperplane is called vertical if the PD plus 1 entry is 0. That's a vertical hyperplane. It's easy to see in in D equals 1, which means D plus 1 equals 2. Because then the defining inequality here is then just, so we have some vector P, which is just P1 and 0, and then the respective hyperplane H P alpha is then just the set of x1, x2, such that this guy vanishes here, this guy just gives P1 times x1 equals alpha. And so what kind of set is this? It's just the set where the value of x1 is pinned down to the value of alpha divided by P1. So this is then this set here. So it's actually, these are vertical hyperplanes. And also this is the vector. Okay, so this is what we call vertical hyperplanes. For PD plus 1 non-zero, we can rewrite this defining equation as so we can kind of rearrange it to xd plus 1 equals, and then we have here minus p prime divided by pd plus 1 with x prime plus alpha divided by pd plus 1. And so what we see is the hyperplane HP alpha as a subset in Rd plus 1 is the graph of the function f from Rd to R, and then x prime maps to this expression here, minus p prime divided by pd plus 1 x prime plus alpha divided by pd plus 1. Okay, so this is one relation between hyperplanes and graphs. Okay, nice. Okay, that was the notion of hyperplane. They will pop up all over the place, and one thing, important thing is if you can, that convex sets will be the intersection of all the hyperplanes which contain it, and this allows us. It's sometimes really important for application, because one immediate consequence is the following. So if you have one point here, and you, for example, want to project this point onto this convex set, but you don't know how to do it, then you can always improve this point by taking any hyperplane which separates this point from the convex set, so for example this one, and project the point onto the hyperplane. And what then happens is that you moved closer to all the points in the set here. So no matter how hyperplane you take, what hyperplane you take, as long as the convex set is on the one side and the points on the other side of the hyperplane, the projection of the hyperplane always brings you closer to every point in the set. That's kind of an important algorithmic principle. Okay, that was hyperplanes. Good. Now come to cones. Okay. Definition 2.1. Actually, I could have used definitions for hyperplanes as well, but anyway. So, some set K in Rd is a cone if, and this is very simple, if we have one point in the cone and a non-negative scalar, then the scaling with this non-negative scalar is again in K. That's what a cone is. Okay, that's okay. So for example, so if we have the R2 here, we have the origin over there, and so this is the origin, and we have one point, and then all positive scalars here are just these guys here. So this, for example, is a very simple cone. If you also have this point here, part of the cone, then we know that this full line also has to be in the cone. So the union of these two half lines here, or half infinite lines, is a cone. Okay, good. Okay, of course, since we're doing convex analysis, convex cones are more interesting, and so convex cone would be like this guy here filled up. This would be then a convex cone. And so convex cones can be readily characterized. Proposition 2.2. The cone K is convex if and only if, so I with a double F, or if with a double F, the sum of the cone with itself is contained in the cone. K plus K is contained in K. Which means that you basically add to this condition here that you can scale positively, arbitrary. You could also add 2 points in the cone and will stay in the cone. That's what this is. So that if you take 2 elements in the cone and add them up, then you will end up in the cone. And this is true for this cone, for example. Okay, this has a simple proof. Let's do this direction first. Let's say cone is convex. And we need to show that this holds here. So we let K CVX cone and take 2 points from the cone, and now we need to show that the sum of them is also in the cone. So by convexity, this implies that x plus y over 2. This is the convex combination. It's x 1/2 times x plus 1/2 times y. This is again in the cone, and by cone implies, so we can scale this by 2. X plus y is in K. Okay, that was simple. And the other direction is also simple. Okay, the other direction goes like let K cone and K plus K subset K and 2 points in K. And now we need to show that an arbitrary convex combination here is again in the cone. And this is very simple because so now we take any lambda in 0, 1, and then we know that lambda times y and 1 minus lambda times x and 1 minus lambda times y are again in K by what I wanted to say is so that the condition that this is the cone implies this. We can we can scale positively. So this is a positive scaling, and this also because lambda is small equals to 1. Okay, and now by K plus K subset K, we have lambda x plus 1 minus lambda y is also in cone, and that's it already. That was fast. Good. Okay. Okay. So, what else? Okay, a list of examples. Example 2.3, and this is a longer list. So first, linear subspaces are convex cones. Linear subspaces are convex cones. More precisely, we can even say K cone is subspace if k is equal to minus k. So if you can flip the cone around the origin and it gives itself, then it's actually subspace. Okay, these this half spaces, if you take alpha to 0, then these kind of this hyperplane goes to the origin, and if you take the positive or negative half space, these are convex cones. All of them. Okay. Another one is the so-called non-negative orthant. Oh, I probably had to miss that one. So this is denoted by Rd and then greater or equal to 0, and this is a set of all x such that all entries are non-negative, is also a CVX convex cone. It's called the non-negative orthant, and in R2 it's just the set up there. Okay. So two more types of cones. If we have sets of the form a times y with y a non-negative vector, and remember this is component-wise, you could also written here x non-negative. So it's kind of the image of the non-negative orthant under a linear map A. It's also a convex cone. We know that already by because it's a linear map, a linear image of a convex set. And of course, A is d times m. Y comes from Rm. This is a convex cone. These are called finitely generated. Okay, good. And a little bit related are the cones of this type. These are all the vectors x, such that A transpose x is non-positive, and with some A which is now m times d, and this x is now an Rd. So these are then a subset in Rd, and this would also be a subset of Rd. Is also a convex cone, and these are called polyhedral. Yeah, and so they are finite intersection of finitely many of half spaces of this type here. Okay, good. Okay, nice. Another one, and I like that cone very much. It's called it's LD+1. It's called Lorentz cone. Unfortunately, not named after me, but anyway, it's a Lorentz cone. In D+1 dimensions, you split up the vector like this again, with d coordinates here and the last one, and then the condition for the Lorentz cone is that the 2 norm of the first d coordinate is bounded by the last coordinate. So that is the Lorentz cone, and it's yeah, I think it's called Lorentz cone because it's kind of related to this space-time contract. Space-time cone, which is kind of the cone which is reached by light rays in the universe, if you consider the 4-dimensional space-time vector space. It's also a convex cone. Yeah, and how does it look like? It looks as follows. So probably we just write it down in 3D. So d equals 2, and then this here reads as x1 squared plus x2 squared. Square root of this is smaller or equal x3. Did I do that font? Do I have a wrong sign here? Let me check. No, seems to be right. Okay, so what is that? So if we write down, well, sketch the R3 here. Yeah, that's right. Okay, so then this set here of all the x1, x2 which fulfills this is first the set with equality is simple to see. The set with equality basically says that x3 is a function of x1, x2, and it's actually the 2 norm. So this gives you a cone is set like this. So this is your 55 degrees, if you like, if you want to say so. And then this is kind of the surface here would be the one where you have equality here, and everything which is inside that thing here, that's the Lorentz cone in 3 dimensions. And this, for this reason, is also called ice cream cone, because it looks a little bit like an ice cream cone. Okay, and then one more. 7th example, also important in a lot of applications, is we call it sim_d plus, and these are the d times d matrices, which are symmetric positively finite. So the set of symmetric matrices which are positively finite, which means, for example, that all the eigenvalues are non-negative, or that xtmx is always non-negative for any x. Okay, this is also a convex cone. It's very simple to see, because it's very simple to see from this condition here. If you take a convex combination of matrices, or the scaling of matrices, it stays fulfilled. So it's a convex cone. Okay, and then actually it's related to the Lorentz cone in 3 space in the 2×2 case, but okay, because 2×2 symmetric matrices are just parameterized by three numbers. X1 on the top left, x2 bottom right, and x3 on the anti-diagonal, for example. And then by a suitable change of variables, you can see that this is kind of related. It's kind of a it's a linear image. It's a linear image of the Lorentz cone, the set of symmetric matrices in 2×2, parameterized by 3 variables. Okay, but anyway. So, okay, and now next definition. This next definition gives kind of the first glimpse of a very important property. So we have several very important principles already. You to see inner outer characterization principle, and then another important principle is duality. It's always good to describe things in 2 different ways, or to some object have a dual object affiliated, which sometimes reveals more structure of the problem, which you can't see in the primal way. And for cones, there's the notion of the so-called polar cone. So, as often is the case, you don't need to start with a cone to be able to define the polar cone. So we just need that S is a non-empty set, and then it's the polar cone of S is S star, and there are different notions of how to denote the polar cone. Let's use the star. This is a set of all vectors P in Rd, and of course this is also a subset Rd, I forgot to say that. All vectors P such that for all x in our set S, it holds that the inner product of P and X is non-positive. Okay. And this is actually the same as the intersection of half spaces Hx0 minus for all x in S. Okay, and so now this is just by definition. That's just every set is of this form here. That's just it. And so we see already that S star is a closed convex cone, because all these sets are closed and convex, and they all pass through the origin, and the intersection of closed convex half spaces which pass through the origin is a cone. Okay. Okay, and what's also important is this inequality here. It stays the same if you divide it like P times F divided by norm P norm X if these are non-zero. So if these are zero, this is meaningless anyway. It's always fulfilled. So it's equivalent in the case Px non-zero. And this is the cosine of the angle between P and X, because we are now have normalized vectors here. So this is exactly the cosine of the angle between P and X. So and this says the following. So if you consider, let me write down or sketch this S as a cone, And I use I realized that because I'm working on paper here, I can use these handy tools here. So if this is origin, and let's say our set S is already a cone, and what's the polar cone? So the polar cone, now geometrically, is the set of all the vectors P which form an angle with x of the cosine of which is negative. And the cosine of these angles negative means that the angle is larger than pi over 2, so larger than 90 degrees. So and how do you construct the polar cone now? Is we take these extremal rays, and they're actually called like this, and do a vector perpendicular to this. So this here is a right angle, and the same for that extremal ray here. And if we do that, this guy here is the polar cone, because if we take one vector from here, and another vector from there, this angle between these guys here is larger than pi over 2. It's larger than 90 degrees. So, and you see the smaller the S, the larger the S star, and so on. And the larger the S, smaller the S star. Okay, good. Good. And we have examples. I'm not sure. Probably we're going to show this in the exercise in the next one. So let's call this effect, and I'm not going to prove it. The effect is if you take, for any set, the polar cone of the polar cone, then you will get not back k, but you would get k back if k would be a closed convex cone. And it's even better, you get always back the convex hull of k and even the closure of that. So this is a way in which, at least mathematically, you can find for a kind of generating set the smallest closed convex cone which contains this set. You just take the set and take the polar cone twice, and then you'll end up with the closed convex hull of this polar cone for any set k. And they already see, so if k is already a closed convex cone, this would be k again, and it's an if and only if. Okay, yeah. And now a list of examples. 2.5. If you have k is just the origin, then this is there's no inequality defining anything, because then the only x which is in S is 0, and then in a product with any p is 0, which is smaller or equal to 0. Then we have that the k star is the full RD. Okay. And the vice versa, if the polar of the RD is just the origin. So what is also interesting is k is a linear subspace. Then the polar, so then it's a cone, it's a convex cone, and the polar is exactly the orthogonal complement. It's also what is written here basically. I mean, so because if k is a linear space, then if x is in the linear space, then minus x is there too. So you have the inequalities. This guy is non-positive and non-negative, so it has to be 0, and so that is all p which are orthogonal to all the x's. Okay. So another example, which is basically could be already deduced from here, if you take a non-positive, positive orthant, a non-negative orthant, so here in R2, it's this set here, and so by this construction it's pretty clear that the polar of this is the non-positive orthant. So this, so basically that's set down here. So these two cones are polar to each other. Okay, fourth example, let's consider a vector p in RD, and as cone we take the negative half space associated to the p through the origin, so because we want to have it as a cone, so all the x such that px is smaller or equal to 0, so it's in half space. And then we basically already see what the polar cone is. It's just written here. So the polar cone is just then everything which is generated, so the non-negative scalings of p. So it's lambda p with lambda non-negative. It's kind of an extreme case of this construction. If this S here collapses to just one vector, the polar would be the full half space orthogonal to this. Okay. Okay, that's one nice thing, and also nice and simple to see is if we have a finitely generated cone, so something which looks like this, then the polar cone is polyhedral. So it's of the form like that. So finite generated and polyhedral are also kind of polar to each other. Okay. Good. Let me see. So what's our time now? We're almost at the half. So and there will be a break again. But I think I'm gonna start with tangential and normal vectors already, and then we'll also kind of formally not clear up the thing. But what I mean by normal. Okay. Definition 2.6. So what we now want to do is to define tangent vectors onto something. And so if let's consider, so we have a set here in 2D, let's say it looks like this, and we have a point here on the boundary, and then so geometrically it's pretty clear what tangential would mean, so it's just a plane which just touches it here, and so these tangential vectors, yeah, they form a cone. They form a cone. So, but this is a smooth point, so it's just a hyperplane, which would be the tangential, the vector of all tangential tangents. So, but what would we do in a point like this here, where there's a kink? What would be tangents in this case here? It's not so clear to me actually what would be considered as a tangent here. Okay, let's define it. So, if you have some subset S of Rd and some x0 which can be in S, so it doesn't have to be at the boundary, the other thing also works, then the so-called tangential cone at x0, tangential to S, is defined as follows. That's all the vectors v in Rd such that there exists a sequence of xn coming from S converging to x0, and also a sequence of positive numbers decaying to 0, such that this v is nothing else than the limit of xn minus x0 divided by lambda n. Okay, so this is the tangential cone. I find it pretty hard to visualize actually. Yeah. Here there's a node missing here. Let me see, can we say... Yeah, so for example, the one thing which is simple to see, and we will see an easier interpretation once we define the normal cone, which I personally find easier to grasp. So if you take a point inside the set, which is not forbidden here, then what is then the tangential cone here? So what vectors can you form like this? And this is then simple. You can just, as xn, you can take, as xn, you can take, so you can approach this vector from any direction, from here, from there, from any direction. So this xn minus x naught can be pointing into any direction. And with this scaling by lambda n, we can kind of scale the limit any way we like. So the tangential cone of this point inside the set is the full space, because basically all directions kind of point inside the set. And in a point like this here, in a corner point, yeah, also in this point, this was different than I explained before. Let's do it again. So let's first deal with the corner point here. So what we need to consider is sequences of xn that approach this x0 and the direction of the vectors from x0 pointing to x0. maybe I might draw a blow up of a kinky point here. So this is a blow up, and so, and if this is now here is our x0, then our sequence xn can approach like this. And then you see that the connecting vectors, you can scale them arbitrarily by dividing by a sequence going to 0. So for example, this one would be a tangent vector in the tangential cone. This one would be 2, but also this one here. And also these guys here. And everything in between. These are all in between. That would be the tangential cone. And in a smooth point, here, this is our x0, then actually the tangential cone would be tangent plane and all this, and the half space, which is the one in which the set C is the set S is contained. Okay, that's the tangential cone. Okay, there's the tangential cone. There was one thing which is I wanted to define too. This is the normalized directions. Normalized directions in the tangential cone are the limits xn minus x0 divided by norm xn minus x0. So, and if then xn goes to x0, xn comes from S arbitrary, then this converges to some why is it like this? I think this should just be V, right? Oh, anyways, these are directions. Okay, it's written like this, and these are all two norms. Okay, and these V's are the normalized directions. Okay. Another characterization. Yeah, and in the case of convex. Yeah, that's right. In the case of convex C, so if C is convex, then the tangential cone can be written differently, and this is basically how I drew them here actually. The tangential cone at some x0 is then just, we take arbitrary vectors, elements of C and non-negative scalars, and then we scale the connection vectors from x to x0. So these are the vectors I drew here. But this is not all, because in this case here, this set would not include this extremal rays. They would not be included because we drew off already, so we need to take the closure of this. So the closure of this set of vectors would then include these two things. This is the convex cone. In this case here, and it's always closed by definition. No, not by definition, but because it's here written as a closure. Okay, that was the first half of the lecture. I think I'm pretty good in time. And actually, looks like this is basically all I had to talk about. Oh no, there's a normal cone is still missing, and then we're done with cones. Okay, so but first there's a break. There's some more jokes for you, and we'll continue in I think 2 minutes or something. Okay, here we go. So, tangential cone. So actually it's simpler to explain than I had in mind. So another definition is the normal cone, which I granted still find it a little bit more intuitive than this one. So, but this we only define this for convex set, so this can be done for any set, but the normal cone is for us it's simpler to define it in convex. There's also a notion of normal cone for non-convex set, but let's do. So C will be convex set, and x naught coming from C, and then the normal cone is NC of x naught. It's defined as, these are all the vectors P such that for all x it holds that x in C, but sorry, x in, for all x in C it holds that, once again, come on, x in C, it holds that the inner product of P with the connecting vector from x naught to x is non-positive. Yep, and maybe I draw an image similar to this close-up here. So let's like this and consider this x naught here. And we already kind of have an impression of what this could be, because this, we already know that this means that some angle is larger than 90 degrees. And which angle is it? So what are the p's now? So we can consider some x here and some connecting vector, and then this p has to have an angle with this x larger than 90 degrees. So it has to be like somewhere here. So there's this hyperplane here. But we have these extremal rays, this one and that one, and then we need, and again I probably should use this guy here. So we could. So the vector p has to lie kind of on this side here of this ray, because we need to be perpendicular to that guy, and again like this. So these are also this here, then that's the normal cone. It points outward kind of, and in smooth points here where the tangent is just like that, then we only have one. So a kind of then the normal cone is just generated by positive scalars, positive scalings of just one vector here. Okay, and so we already saw it here by proof by picture. The following theorem is that the normal cone and the tangent cone are polar to each other. So, but this only holds if C is convex, x0 is in C. And then we have, let's see again, that the polar of the tangential cone is the normal cone. Well, so by picture it's clear. Probably the one thing is, what about the closure here? Yeah, let's do the proof. And first start with P is in the polar, and then we need to prove that it's already in here, also in here. So kind of we do this inclusion here. So this means then that P times V is non-positive for all V in the tangential cone. That's just the definition of the polar. But here we can use this characterization of the tangential cone, and so we see by limits. So we can write every element here as the limit of expressions of this thing here, and the t is non-negative, so you can multiply the inequality through by t and don't see it. So that's basically it. So this is kind of the same as use this, the v's here, the v's of that form, and so the t doesn't matter, or limit of that form. But anyway, we see that p times x minus x naught has to be non-positive also. And conversely, if we have a p in the normal cone, we have show is that P times V is non-positive for V and tangential cone. And so this V is then by this here of the form limit of, by this definition actually, xn minus x naught divided by lambda n. And this xn has to converge to x, and the lambda has to go to 0 from above. But if you plug this in here, you can again multiply through by lambda because it's non-negative. You don't flip the sign. So this implies that p times xn minus x naught is non-positive. So by this here, and so now you can. This does not apply. So this is given because we are in the normal cone, and if we now pass to the limit, we'll see that this implies that p times v is also non-negative because the scalar here is non-negative. Okay, that works. So and that was that about cones. For now, maybe cones will come back later on. Okay, but we still have half an hour left, and that's good because we still can start introducing orthonormal or orthogonal projections. Okay, so orthogonal projections, you probably know them from linear algebra, that for every linear space you can project onto this, and you can do this by solving the normal equations, for example, and orthonormal projections are unique and stuff. And a lot of things also hold here for projection onto convex sets. Theorem 2.9. And this is the so-called projection theorem. So this one has a name, not named after some guy, but it's a projection theorem. So it goes like this. If you have C in RD, non-empty, closed, and convex, and then we can show that for every x naught in RD there exists exactly one x naught hat in C, such that the distance from x naught to x naught hat 2 norm is equal to the infimum of all distances from all vectors x in C. So it's kind of the closest point. So which means, so if you have your convex set C and you have any point x naught in here, then the if under the assumption of non-emptiness of this closeness and convexity of C, there's exactly one closest vector here of C which is closest to x naught. And this is this guy here. Of course, you see without convexity you would not have uniqueness, because so the set may also be located here, so why not? Maybe. But then the set would not be convex anymore. And without closeness you wouldn't have existence, because it just maybe, so if you just remove the boundary here, then it would be open and they would not exist. So the infimum would still be attained, but the infimum would still exist because an infimum, but it would not be attained by some vector. That's what I want to say. Okay, and this is this x naught hat is usually defined like this. So PC always stands for the projection onto C, so onto this orthogonal projection. Yeah, and this is in the orthogonal projection. Okay, but that's not the end of the story. That's not the full projection theorem. There's even a characterization. It holds that so this x naught hat fulfills a so-called variation inequality, and that for all x in C it holds that the inner product with x naught minus x naught hat and x minus x naught hat, this is non-positive. And we already know that's an angle condition here. And this is important now. Because so this gives you the view of the orthogonal projection as moving to the on the shortest route towards C, closest point which you can find. But this says something else. This says that if you take a point in X in C, and then this guy here is actually it's bad. Probably why it's like this. I would write it like that. So flip both signs around. But it's the same thing, because if we do it like this, we would have that would be this connection vector and this would be that connection vector. And what is written here is that the angle here has to be larger than 90 degrees. Okay, and so this is obviously it's fulfilled. So if you try to project here, then you get angles which are smaller than 90 degrees. But it's also characterizing. Conversely, if y fulfills that for all x in C it holds that, and now it's again written like this: x minus y, x naught minus y and x minus y is non-positive, then y is actually the projection. So this inequality here, so this so-called variation inequality, characterizes the orthonormal projection. Okay, so that's good. Yeah. Good. So let's prove it. Okay. So there's a lot of things to prove. First, let's start with existence here. Why does there exist a solution of this problem here? And this follows just by, if you consider this f like that, that's a continuous function. Norms are continuous. Okay. And C is closed. What is more is then, so you want to find the infimum of a continuous function over a closed set, and this exists. So infimum exists, and in fact we would need compactness for this, but we could consider C intersected with a large ball around x0, which is then compact, because it's closed and this is now bounded, so we can consider this, and this infimum exists and is assumed, and then assumed by Weierstraße, or attained by the general theorem of Weierstraße. And yeah, probably that's enough for here. So this shows existence of projection. Projection exists. Okay. And I think what we're going to do is we do uniqueness last. So first, so this shows existence, and let's do characterization, and then in the end we do uniqueness. Okay, characterization. This is the point. First point. Second point of the proof is let x0 had be defined as the projection of x0, and because C is convex, we have that the connection, so this is an let me see. So this is, by definition, this is an element of C, and by convexity we can take any C, any x in the set C, and take then the connecting line, which is x0 hat plus lambda x minus x0 hat. This is then again in C, and lambda in 0, 1. Okay, good. Okay, and now we know that f, this f from here, is minimal at x naught hat. And this means that if we plug in, so if we consider, if you plug in this guy here, over here, oh, there's probably a typo. Yeah, there's a typo, another one. So we plug this guy in over here, we get x naught plus lambda x minus x naught hat minus x naught hat squared minus, so this one is larger than what we get when if we plug in x naught hat, because that gives the smallest. So this is positive. Okay. Yes. Like that. So what we do now is we rearrange. We do. Oh, I'm off screen. Once again. So what we did. So this is f evaluated at that point. This is f evaluated at that point. F assumes its minimum at this point. So this difference here is positive, not negative. Okay. So now we do. Kind of Pythagoras on this term here, and we group it like that and with this. And if you do Pythagoras here, you will get this term again, and this drops because it's subtracted, and you will see you will end up with lambda squared times the norm of x minus x naught hat, 2 norm squared minus 2 times lambda times x minus x naught hat. There's no hat here. Sorry, there should be no head. There's no head there. There should be no head here. So this is no head. And then what's left will be x naught head. Oh, there's more typos here. This, if you do this, we have a plus, so there should be a plus here. X naught head minus x naught. And the third term here cancels out with that. Okay, now we have lambda is non-negative, so we can we bring this guy to the other side. Oh, and then we should flip the sign over here. We can divide by lambda and then let lambda go to 0. So first, since lambda is, therefore we take lambda positive here, which we can do. And we end up with, and we arrange it to, so I flip one of the signs here, x naught hat minus x naught from there, and then x naught hat minus x is smaller equal to, and it remains lambda over 2 times the norm of x minus x naught hat. And so this goes to 0 for lambda to 0. And this shows that this inner product is negative just as it should. Okay, that was this direction. So if x naught hat is the projection, then we have this variation inequality for all x and c. So now conversely to this point, assume that this holds for all x such and such, and you want to show holds for some y, and you want to show that y is in fact the orthogonal projection. Okay, then we can, so we write down what we know. We know that this inequality holds with it there. This inequality holds always. So 0 is larger equal to, and then again it seems like here both have been flipped, so we take y minus x naught and y minus x. What we do here is we add a nutritious null, meaning we add and subtract here, so we subtract x naught and add it again, and then what we see here is we have the norm squared of this guy already, y minus x naught squared, and plus the inner product of y minus x naught and x naught minus x. Okay, and now we do Cauchy-Schwarz in this direction here. So the inner product, the absolute value of the inner product is like this, right? And so if you drop the absolute value, you can have both signs here either way. So another way to write this would be like that. So, and we're going to use this on this term here. I'm getting x minus x naught squared minus the norm of x minus y minus x naught minus times x naught minus x. Okay, and now we are done. If we bring this to the other side and divide by this term here, and we're going to see that x minus x naught minus x is larger or equal to y minus x naught. And this holds yeah, for all x and c, because this is what our variation inequality up here says. And this means that the y is minimizes this. Okay, y is actually the orthonormal projection onto c from x naught. Okay, number 6, page number 7, a lot of material actually. And finally, last point is uniqueness. Uniqueness goes like this. Let's say we have two x hat and x tilde, both orthonormal projections. So then they both are in the set C. And what we now do is we plug them into the variation and inequality of each other. So both x hat and x naught fulfill these inequality, and so we can write this down with y replaced by x hat, and for x we can use x naught tilde, and the other way around. So start in two ways. Then reads like here we use as y we use x hat, and for x we can use x naught tilde. So this is non-negative. And the other way around, we can use here x naught tilde and here x naught hat. Okay, so now we have two inequalities. They both hold, and we're adding both of this. So we can add some, so we have to flip one sign, and yeah, we can add them both. So 0 is larger or equal to. So to make these two things the same thing, we flip that over here. Yep. And while we do it, then we also flip it over here. No, yeah, we flip both so that it stays like this. So let's just write it down. And so if you flip both, yeah, we flip both, then it's look x naught tilde minus x naught and x naught tilde minus x naught hat. And now we see, so we have these and this is now equal. And if we add this guy over here, the x naught cancels out and this stays positive, this is negative. And then we have x naught tilde minus x naught hat again on the left hand side. So this exactly evaluates to x naught tilde minus x naught hat norm squared. So the norm is non-positive. This means that these things are actually the same. And that's one thing which always annoys me about the convex analysis. You always have to really take good care of all the signs and all the expressions. This is annoying because I tend to make a lot of errors in here, and then sometimes we arrive at results which look plausible and often sometimes are not wrong, but it's not what you want to have. So if I would have made a sign error here, I would have arrived at this is non-negative, which is true, and I would have thought, well, this is not working. But taking good care of all signs, you end up with the right inequality, and this really gives you something. Okay. So if you want to do convex analysis, you need to be careful with signs. Okay, and now finally we still have 50 minutes left. This is enough time for all our examples of orthogonal projection examples. 2.10. Okay, and what we do is we project onto balls. So on the p balls. But this is in general a very hard thing to do, but in 3 cases it's not, and these 3 cases are the 1 norm, the 2 norm, and the infinity norm. In these 3 cases it's simple. And we start from large to small. The infinity norm is probably the simplest case. So then this infinity norm ball of radius lambda around 0, we like to take the around 0 because it's then simplest. This is just the vectors x such that all these coordinates are smaller equal to lambda. So these look like this. Okay, so we have that's the infinity norm ball in 2 dimensions. So what is the closest vector now? So if we have some vector over here, which one is the closest in the set? And what is the answer for, let's say, that point here, which is the closest? For that one, it's probably obvious that it should be this guy here. And for this one, yeah, it should be that one here. It should be exactly the corner. And that's actually the same. If I would take that point over here, it would project to the same point there. So basically everything which is in this guy there project onto the corner, and everything else projects directly onto the side. That's geometrically, it's pretty simple. So the space kind of decomposes into different areas, and these corner areas project to the corner here. This projects to this corner, this projects to that corner, and to that corner, and in between it just projects to the side by just moving there. So what you need to do is you need to minimize x minus y squared over all y in b lambda infinity 0. What does that mean? You have to minimize this quantity over all y such that these inequalities fulfill. So what comes out has to be at most lambda here in all its components. And then if you write this down here, write this like this, it's just xi minus yi. And you see that this decouples over all the I. So you need to find, so for one given xi, you need to find the yi, which is at most lambda by magnitude, and which is closest to xi. And this is pretty clear. Then what you need to do, you need to go as much into the direction of xi as you can do. So this brings you to the following: the projection onto the lambda ball with respect to infinity around 0 of some vector x. The ith component of this is either it stays xi if the xi is already smaller equal to lambda, because then you can just take yi equal to xi, and if not, you take lambda but with the correct sign, and this is the sign, the same sign of xi if xi is larger than lambda. Yeah, that's it, and that's exactly what happens up here. And you can write this conveniently in vector form by using the max and min operations. So you can write it like min and max of x and minus lambda and plus lambda. So this, if x is smaller than, so this, you have to understand this component-wise. So that's a vector with components, and this is a scalar, and you broadcast the scalar to a vector. If x, the entry of x is smaller than minus lambda, you set it to minus lambda. If it's larger, it stays as it is, and the same happens in the upper bound. So kind of component-wise, you apply just this function here. So minus lambda here and plus lambda over there. This is what you just do to every component. And then you get the projection onto the infinity ball. Okay, nice. Projection onto the 2 ball. That's probably simpler, huh? Let's draw a 2 ball. Let's see if I can do that. It's actually simpler on the blackboard to write because you have kind of your arm gives you a compass already. So what this is not that bad. Okay, so what is the projection now? Of course, so if you're inside here, you stay where you are. That's always the case. But what happens to a point like that? Where does that go to? And this is then not that bad. We just need to scale the point. So you just move toward the origin on the straight line towards the origin, because then this is here the orthogonal. This is in the tangent plane. Yeah, and if you have another point, let's say over here, you do the same thing. You just connect to the origin. So you move towards the origin as long as you're outside, and then you go over there. So maybe this is just clear from geometry, and I don't write down any proof of this. Actually, the proof is also not complicated, but the projection of the 2 norm ball of x is then either it's x if the 2 norm is already small enough, and if not, you need to find the right scaling factor such that the scaling is already inside the ball here, and the scaling factor is lambda times lambda over the 2 norm. 2 norm, not 2 norm squared, so just the 2 norm times x, in case the norm of x is larger than lambda. And you see the norm of this guy is exactly lambda as it should. Okay, you can also, this is an equal quality summation, you can also write this conveniently with the help of the max operator, like max of 1 or x divided, lambda divided by norm x times x. So it's also a little bit cleaner, you don't need, so you can use the max to take care of the case distinctions. Okay, so what about the case p equals 1? Okay, for p equals 1, the 2-dimensional picture is simple. So in this case, the picture is simple in all dimensions. So in larger dimensions, this ball here has an exponentially large number of corners. So here it has 2 to the d corners. So the space decomposes into a lot of subregions where different things happen. But the formula is always very simple. You just apply this to every component, so it's very clear what happens. Although the object kind of gets complicated because it has a lot of corners, but it's very simple in the sense that you only need a very small number of hyperplanes to describe it, of half spaces. You only in each direction you only need 2 half spaces to describe the thing here. So the number of half spaces you need to describe this guy here is just 2D. So the 1 ball, the norm ball with respect to the 1 norm looks like this. Whoops. And whoops, it should be here. And if you now think about, so actually it looks like the same thing turned here, right? But that's just a special case in 2 dimensions. In higher dimensions, these 2 objects are very, very different. Because of what? So what are the number of corners here? It's 2 to the d. What is the number of corners here if you're in d dimensions? It's just 2d. In every coordinate axis, you have just 2 corners, and that's it. 1 corner here, and there, and there, and there. So this is a linear number of corners, and this is an exponential number of corners. So it's very, very different objects. And so the number of sides here is 2d, and the number of sides here, I guess it's 1 per orthant, so it should be 2 to the d, I guess. Yeah, I think so. Yeah, kind of for every corner here, you have a side of that guy. So they're kind of really on opposite sides of the spectrum here. But here the projection here is then again simple. At least graphically, it's not that hard because you only need to know these kind of lines here. So it's just this picture turn, but it's only in 2 dimensions. But anyway, anything which is here is projected there, and anything else is projected like this. But this is just geometrically. But what happens by formula? And it turns out it's complicated. it's complicated. So one thing is clear. If I start writing it down, the projection onto the lambda ball for the one norm around 0 of x. So one thing is always clear. It's stay where you are if the one norm is smaller or equal to the lambda already. So, but what happens here in the case where the one norm is larger than lambda? So you're outside of the ball. So in okay, let's try. So in this cases here, it's not that hard, because what you do is you subtract the same thing from all coordinates. So kind of you move like this and like this. So if you move here in the 45-degree angle, moving along the path here, you subtract a number or the same number from all components. So this thing here, this vector here arises, you take the vector x1, x2 and turn it to the vector x1 minus mu and x1 minus mu. So this one here is, if this one is x1, x2, then this one here is x1 minus mu and x2 minus mu for some mu, and the mu is actually this distance here. So a mu such that, yeah, the one norm of this guy is lambda. And that's a nonlinear equation which you need to solve. Okay, so but you can do it by line search. It's just one parameter which you need to find, and that's how it is here. In these areas here, it's basically the same, but you need to switch signs. So if you move in this direction, you reduce the first coordinate, but you increase the second coordinate. So here it's basically the same, but with sign flips in front of you, and the same for all the other 4 areas here. Okay. But what happens here in these areas? In these areas, you can imagine that you do the same thing. So you reduce all coordinates by the same amount, but then you're going to hit one of the coordinate axes, which means one of the coordinates you already gets 0. And if this happens, that you don't reach the one ball by this procedure, but you first hit a coordinate axis, then you just move, then you stop reducing this one coordinate. In this case, the first coordinate already hits 0. Then you just you keep it at 0 and reduce the rest until you're here at the point where you want to project to. So this is, it's correct, but what really kind of happens, at least in my head, is you reduce all the coordinates, then you hit 0, and then you fix this coordinate at 0, and then you move again like this. And this is true in all dimensions. But what is really difficult now is to figure out what is the amount of reduction you need. So, but what is true is the following. You can always have one single operation here, s, and they call it mu of x. And this s here is the following operation. This s mu of x, it does the following. It's also defined by max. It's the absolute value applied component-wise minus mu, and then the maximum. Different way of putting this would be if you kind of expand what's the max operator, there's something missing, and times the sine of x. And what's happening here is that if x I is larger or equal to lambda, you subtract lambda. If I is smaller or equal than minus lambda, you add lambda, and otherwise you take 0. So you apply this function component-wise, and the function looks like this. This is the function s. That mu equals lambda, so these are all mu's. Mu. So what is kind of clear from the picture here, that this is true, but for what mu? You need to find a mu. And that is complicated because you don't know a priori in which case you are. Do you need to reduce mu all the way down, or do you or are you in this case here? So one thing is pretty clear, it's just a one-dimensional problem now. Oh, over time. I'm done already. So one thing is clear, it's just a one-dimensional problem. You can just kind of find it by bisection. Start with a large mu. If you're small enough already, then you're good. If not, increase. So because you need to find the mu, which solves this equation here. You can solve it by bisection, which may be time consuming. You can solve it faster, and it's still, people come up with new algorithms for this, but it's basically that the complexity. So the one thing is you could sort the vector and then it would be simpler. But anyway, I'm not going to detail about this, but this is, yeah, this is sometimes, this is important and will be helpful for application, as we will see probably later in the lecture. Okay, I already went a minute overtime, sorry for that. Thanks for listening, and don't forget to reply to this poll here, and we'll see next Monday. So that's it. Bye.